Welcome to Engineering Tomorrow. It's wonderful to be here with you today as we discuss engineering in medicine. And as you can see from the slides, we're going to be talking a little bit about biomedical engineering today and how it can help different people enhance their lives. So, thinking about that particular question, I'm curious, what do you feel is the greatest invention in the medical field? Do you think that it is vaccines? Perhaps it's MRI machines, or maybe antibiotics. Let me know what you think. Okay, so let me take a moment and share a little bit about my engineering background and how I came to work with Engineering Tomorrow. So as you can see on the screen, I was this curious toddler. I loved taking things apart. I really enjoy seeing how things work and trying to reverse engineer them, which meant I took a lot of things apart in my house. I took apart our telephone. It was one of those rotary kinds where you unscrew them and check out all the wiring. I took apart our computer, but the very worst thing I ever took apart was our car door. And if you've seen me before, you know that my poor mother had to hold that car door shut and drive us home, and it was so bad. However, instead of just taking things apart, I decided to join the space industry and to try to make things for our country to help us advance to the next levels. So I joined the space program. I went to Purdue University where I studied aeronautical and astronautical engineering. And you can see here, I have something attached to Purdue. It's NASA Langley Research Center. So if you're watching this, you may be in high school. And I'm telling you this because I was only a sophomore in college as I began working my co-op engineer position with NASA Langley. I was studying how the air effects were, going over the different airfoils for airplanes and things like that. And I remember sitting in my college classrooms and thinking, why is my professor telling me this? I know it's important, but how does it all relate? And what was so cool about the co-op program was that I got to go to NASA the very next semester, and I got to see where the teams were placing the different sensors on the F-18 models and testing it in the wind tunnels. So if you ever have the opportunity to do something like a co-op, or an internship, I highly recommend it. It not only gives you some great context when you get out of school, but it also helps you just see how things relate and work together. And it gives you that added knowledge as to why you're learning the theory you are in your classes. As you know, though, I was so excited about space that when I graduated, I decided to work at NASA Johnson Space Center. That's the one down in Texas. You probably have heard that Houston, we have a problem. That comes from Houston Mission Control down there. So as right out of school, I was doing training for the guidance, navigation, and control system for the International Space Station. So that's a lot of words, right? And with NASA, everything has to have an acronym. So it was GNC, Guidance, Navigation, and Control. So if you can imagine the space station orienting with respect to the stars, or performing reboost, that was what I was teaching our astronauts and our flight controllers, preparing us for flight. In doing that job, I had to work a lot with the Russian computer systems to make sure their thrusters were working in conjunction with our control moment gyros. And so I was asked to become a Russian training integration instructor, RTI for short, where I got to travel over to Star City, Russia. I know it sounds like something right out of Batman, doesn't it? Star City. That's where the cosmonauts have their training center. And it was my job as a RTI over there to help our astronauts learn the various systems of the Russian segment on the space station, as well as the Soyuz. So I got to do amazing things like learning how we clean out carbon dioxide out of the air, or learn how we do rendezvous and docking with the Soyuz in progress, and help teach our astronauts in these areas. When I came back to the States after that job, I joined the astronaut office as their chief engineer for exploration, and I did that job for about 8 years. Down here on the left is Artemis. I hope you have heard about Artemis. We are living in such a cool time, you guys. Artemis is when I'm recording this, currently up on orbit right now, doing a distant retrograde orbit of the moon. And then on the right, you can see SpaceX and Boeing. So these are our commercial crew programs. And you can see these are the ones that are taking our astronauts mainly to the International Space Station these days. So it was a pleasure and joy working with the engineering teams at both Johnson Space Center and Langley, as well as working with our Russian colleagues over my career. But that's enough about me. I am here for you guys today, and I want to introduce you to our medical engineering lab. Part one, we're going to begin talking about how medicine is included in our engineering world. So let's go. On the left, you can see we have Christine Boothill, and she was the lead engineer who was helping to create this particular lab. On the right, we have a group of college interns and mentors that have also helped to create this, Emma and Dylan. And when you have your Q&A sessions, you may even get the opportunity to talk with them about this particular lab or what college life is like in general. So engineering in medicine is also what we call biomedical engineering. When we talk about medicine in the human form, that's when you would see biomedical engineering. If we talk about it in plants and animals, it would be that higher level of what we would call bioengineering or biological engineering. So biomedical is the application of engineering principles and design concepts to medicine and biology for healthcare purposes. So we're talking here how to help someone either prolong their life, reduce certain symptoms that they're experiencing, or just give them enhancements. What we're going to do today, which is so cool, we're going to help make prosthetics for people that need them. So you can see here, biomedical engineers design and analyze all kinds of things. Like I said, prosthetics and braces. That's what we're here for today. And you guys get to be that biomedical engineer in today's lab, which is so cool. Other things like surgical devices and medical models, being able to model that human body, look over here on the right, and to know where every joint and ligament and all of those are placed and how they work together in order to create different devices. Here's one, medical and dental devices. Sometimes we overlook the teeth because we think of dentist and we don't think of the medical doctor, but those are also medical devices. So if you've ever worn braces or maybe had a retainer, you've benefited from those parts of biomedical engineering as well. We have medicine and treatments, cell and tissues. You guys, it is so cool. I was looking at pictures of being able to 3D print different types of tissues and cells. Let's take a look. 3D printing has really changed the world. You can see here, I've highlighted 3 words. They make it cheap, customizable, and fast. That's so helpful for any kind of patient that we may have. You can see down here, we see some of those dental ones that we were just talking about. So maybe you've had to wear Invisalign as kind of braces for your teeth, or maybe you needed an actual implant of some of those bones. And here you can see things that affect our hearing, some of those cochlear implants and all of those other devices that are helping improve these people's lives. Can you imagine being able to see the reaction of someone being able to hear for the very first time in their lives? How incredible, and how incredible to be a part of it. So let's take a look at this particular video. You will notice the changes in life that are being provided by 3D printing and prosthetics. Here we go.
What it was like before having this hand, or like having like any hand, it was pretty hard. I get bullied a lot, and like I really wanted to be part of a team. I wanted to have friends. I wanted to act like I actually had like a right hand, and it wouldn't really care if I had that.
Enable is an online global community of volunteers who are using 3D printers and 3D design software to make prosthetics for children and adults who are missing fingers, hands, and wrists, and we're giving them away for free.
One of the reasons 3D printing is so well suited to this problem is no two cases are exactly the same. Some kids are missing all of their fingers, some are missing even the palm and the wrist. One of the reasons we can produce these devices in kind of incredibly low cost, well under $100, is these devices are entirely body-driven, purely mechanical, so there are no motors, there are no sensors, there are no heavy batteries. So it's a very lightweight, very simple device.
These hands don't even pretend to look like normal hands. They're very different. These things look like something Iron Man or a superhero would have, and the kids love them for that reason.
Once I had this hand, my friends would ask, "Hey, dude, how's it going? Has anything changed with it? Is it working better?" And it's pretty cool how they're actually involved. They're actually talking to me about it, and I love this because I could pick up stuff and I could help.
It's been really great to have Kieran and his family come to Pier 9, to prototype these new ideas, to test drive these new hands, and to be able to see the higher perspective, what this is all about, to see how that hour of CAD, translated into him being able to hold his coat or zip a zipper better.
What Enable has done is it seems that they've kind of proven that regular people can design amazing things if they're given access to the tools.
I think it's pretty cool that I'm one of the people actually testing this out for a bunch of other people. It's gonna be really awesome to see it when it's so big. Every kid that has a problem like me will have a hand.
Wasn't that video incredible? Look at that boy and think about how his life changed, how he was able to pick up something for the first time in his life and help out in the kitchen, using that blender, being able to hold the top on and press it to start. Those are things that we, sometimes can take for granted. And it is so amazing that today we are going to take a look more deeply at what Enable does and try to be a part of it ourselves. So on the screen, you can see Enable is using tension strings attached to the wrist and joint and socket at the base of the finger. Notice this here, it kind of goes around like a bracelet that you're seeing. When 3D printed pieces are acting as bones, we can't just print out 3 and then have them stiff. We have to be able to use our fingers. So if you take a look at your own hand, notice how each joint of your finger is moving. When certain people need fingers, you're going to have to print out each joint in order to be able to help them with this. And each joint is then connected with a pin. So that pin will allow that movement that your finger so easily and normally does. Depending on how your patient, what kind of limbs they may have or the attachments, you will have to think, does my attachment need a socket for them to be able to put the limb into so that it can attach in that respect? Or is a bracelet enough? So I want you to think about these things because it's going to be important in how you create your design today. Here's some other angles. I like this because you can kind of get a feel for what I was talking about with those pins and those tension strings. So imagine this hand having different strings running up these holes. Those strings, almost like rubber bands, are helping to perform what our muscles and our ligaments are doing for our fingers. So as there is tension on those strings, you can imagine if you're able to pull tension on just one, your one finger can move. In your lab today, it will be your job in order to build one finger. But you can see how quickly and easily you could make a whole hand if you so choose, which is so amazing. Over here on the left, I like this view as well because you can kind of imagine each of these being a separate, a separate part of the finger, and you would have your pins going perpendicular through here to allow that rotation that you see. Let's jump right into part 2. How about it? 3D printing in the product development process. So there's lots of different ways of representing like how we do different engineering processes. You can see here one way that we represent it. There's the product manager. It's usually the person that comes up with an idea and wants to take this idea to fruition. So next would be the design engineer. This person would be responsible for researching, are there patents out there? Are there other designs that we could build off of and make them better or to alter them slightly to achieve our goals? And then the materials engineer. This person would be the one studying, is a person able to have this type of 3D printed material up against their body? Our skins can be very sensitive. So is it something that's going to be friction or cause friction and friction points? Or is there a way that we can use a different material that will be less corrosive to a human, that will be biocompatible with what we as humans might need? On the right here, you can see the manufacturing engineer, the person being able to build it over and over and to produce this for many people. And then on the right, quality engineers. So testing it. I love testing things. As an engineer, it's one of my favorite things to do. So why do you think we might want to use computer-aided design? I mean, we could use our pen and paper and sketch it out, correct? No problem, we could do that. However, if we want to build something, and maybe we want to be able to scale it, maybe we're building it for a child who is growing, and we need a particular hand or finger created, but in 3, 4, 5 months, a year, they're going to need a bigger size. So having their particular dimensions and then being able to size it up very quickly and easily in CAD can help save time, but also give them what they need without having to use something that is not the right size for them as they're growing. So that is a huge time saver with computer-aided design, but also you can be so specific. Being able to design something using software, you can easily modify it for one patient to another and save your files and let it be customizable and personal for them. So let's take a look at CAD. Many of you may be very familiar with how CAD works and engineering drawings in general. So when we go to produce a piece of equipment, we need some detailed drawings. We're gonna need to know, what does it look like? So you can see over here on the right, that isometric view gives you that 3D feel that you're used to seeing, or at least in my brain. It makes conceptual sense to me when I look at it. But then there are some other views that can be super helpful in engineering as well. You can see that we also would include something like a top view. When you look at the top view, you get specific dimensions of what is different from the top versus the side versus the front. And that can be helpful as we're trying to create something with very tight specifications. We don't want to create a finger and have it be great in the length, but wrong in the width per se. So having these different views can be super helpful. This one being the top, you can see over there. And then also that front and then the side views as well. Notice that every engineering drawing should have dimensions. Dimensions can be very key because you will see in just a few slides that if we don't include our dimensions, the piece of equipment may be something totally different than what we're expecting. So this is considered like a universal language that engineers and production managers use to help create certain things. This all goes into what I would consider something like spatial intelligence or spatial awareness. Being able to understand what something is going to look like from an aerial view from, Google Earth versus driving in your car. So having those different concepts and views and maps in your mind are what people might consider spatial intelligence. and being able to adapt those 2D views into 3D and vice versa. Can you think of any fields where this might be helpful? You can see that architects, people who have to build buildings or different structures in a given space, they have to have that good awareness. But not only like engineers, but also photographers. I don't know if you guys have heard about the photographer and filmmakers that are now using drones so that they can capture just the right views as they're making their movies and different pictures and shots. It's pretty cool. Graphic designers, people who have to be able to lay out a given view of what they're trying to convey. And that goes right along with fashion designers as well. If you have ever known to walk through a mall and see the store displays, those designers have had to think about how you're walking, the angle that you'll be viewing it at, and what's the best thing to look at. And then my very favorite, this is just my personal favorite, is the astronomers. Being able to understand like how those planets are oriented with respect to each other and how the stars are located in the sky, and how as planets are moving, how that view changes. There are some really cool videos out there right now about Artemis and how it's able to view itself, Earth, and the moon all in one shot. So if you haven't seen them, take a look. All right, so let's practice. Are you guys ready? So this is a piece of equipment. I want you to imagine that you are getting ready to design this attachment here. And I'm curious, which one do you think this is? Do you think that it is the top, side, or the front? What do you think? All right, I have one more for you. Are you ready? How about this one? What do you think that is showing you? Is that the top, the front, or the side? For those of you that had guessed, for the first one, front, and for the second one, top, you are spot on. High fives. Okay, let's get to it then. Remember I was telling you about dimensions and the importance of being able to see things in multiple ways? So if I showed you this design, what do you think it is? It's kind of hard to say, isn't it? You know, I can see a couple dimensions here, but all I see is a block. There must be more to it, right? Check it out. This is actually a tissue box. But looking at it from the bottom, you wouldn't know that. You might just think it's a brick or some other piece of equipment. Looking at it from all these other views, you can see the cutout for the tissues to go into, kind of the radius that it has, and, you know, the depth and width and height, different aspects. So you can see here it's in inches, it's not in feet or something incredibly huge, right? Let's take a look at this one. What do you think this could be? It's a little hard to say, isn't it? If I add these dimensions, does that help you? What do you think it might be now? 7 inches high, 5 inches wide. What do you think? 10 inches long. Yeah, if you guessed a step stool, you were right on. Good job. All right, here I changed the dimensions on you. Did you see that? Now, instead of just a few inches, we're talking 30 feet long. Do you think that's still a step stool? 21 feet high? I don't know about you guys, but I can't step up that high. I wish I could. So in this particular one, you are looking at a bridge. So if you had said a bridge in the first one when we had no dimensions, you would have been right as well. Look at you guys, you're rocking it. All right, so here comes your part. We're into part 3 now. It's your turn. We're gonna start making the prosthetic. What you're gonna do is familiarize yourself with some of those enable, prosthetics that are out there. You know, what kind of hands are there? What kind of fingers are there? What are their sizes? And then from that, you're gonna gain an understanding of kind of how these fingers are working. You'll choose a finger. I want you to think about which finger do you want it to be? You know, is it gonna be the pinky? Is it gonna be the forefinger? Who are you making it for? Are you making it for someone that is growing, or is it going to have to be scalable? And you're going to start by drawing a 1-to-1 scale sketch of your chosen finger. And then, so when I say sketch, I would probably do this out on paper first, because when you do something on paper or cardboard, you're able to make a quick prototype. And I'll show you here in just a second how that can help you. One constraint I want to list out before you get there is that if you're having Engineering Tomorrow print your fingers, definitely keep it to these dimensions, 10 centimeters by 10 centimeters by 2 centimeters. This is so that we can print out several of your projects and get them back to your school in a timely manner. If you're printing them out in your own class with your own printers, talk to your teacher. They'll be able to tell you what dimensions they're able to process in a timely manner for you. All right, with that said, here we go. We have certain constraints for designs, right? Do you think they're a good thing or a bad thing? Are they always bad? Sometimes I hear the word constraints and I think, oh no, that sounds bad. But in reality, as an engineer, they can be super helpful. So knowing how much money we have to create a particular item, whether it be the finger, the hand, or something like a spaceship, how much do we have? What are we working with here? What quality do we have to have it in? Does it have to be within a half a centimeter or a half an inch? What is the tolerances we can handle? You can see down here this famous quote from Winston Churchill: "Perfection is the enemy of progress." And what that means is if we try to make something so perfect, we can get stuck or keep over and over, redoing it over and over again to the point where we're actually not getting it out to our, person that needs it, our clients. So making sure it's good enough and that it meets all the needs. So you want to make sure that it's doing what it needs to do, but that we're doing it in a timely manner as well. We don't want to make a prosthetic hand or a prosthetic finger and have it take 6 to 10 months. If that child is growing, they might already be past that point and need the next one already. So what time constraints do we have? Or if you're building a spaceship, when do we need to launch by? What's the launch windows that we have to be ready by? So time, cost, and quality constraints can be your friend, especially in the engineering world. It lets you know what you're working with and how you can proceed. Here is a quick prototype. Remember when I said sketching? If you're considering sketching first, I highly recommend it because you get to understand how it all fits together, how those ligaments are working. This person had used a piece of cardboard. It looks like it came straight from our Engineering Tomorrow products, you can see, and they have cut out the hand. Next, they have used different strings or pieces of elastic to help show the tendons here. You can see how all that's fitting together. And then once you have this creation, you will know what you need to do in order to either connect it to your patient. Does it need to be a socket? Or what things you need to do to connect are different pieces of string or elastic to help create the movement for these fingers. Here we are. Let's jump right into some Tinkercad if you're ready. Now I am looking at my Tinkercad screen and you can see here I just pulled in a cylinder. I'm just going to give you some basics in Tinkercad to think about as you're creating your particular finger. I'm going to locate it wherever it feels comfortable in your work plane, anywhere you want. If you're noticing that it's solid or a color, like mine is orange, that's good. That means it's something that will be printed out. If you notice that it's hashed, that will mean that you're subtracting that part. So for now, I'm just going to start off with a joint. Here is my particular first joint, I'm going to say. It looks a little bit big, so maybe I'll kind of squish it down a little. And then because fingers aren't so round, they're a little round, but I think we need to kind of help flatten it out a little bit. I'll bring in this cube over here. Notice I just grab it and pull it in. As I'm pulling it in, you can see the shadow appearing on that side of the finger there, right? When I like the placement, I can go ahead and group these together. When I group them together, it will subtract this gray part from the solid finger part. I'm going to hold off on doing that because I want to make sure that I get the other side equal, and I want to make sure that I use the same kind of block that I'm using. So I'm just going to do a Control C and a Control V to copy it, just like you would in Word or any other Google type of thing. And so now I can ensure that I'm getting it fairly close, right? You can move these up or down however you want. That's what I love about Tinkercad. It's so easy and so quick. Once I get it where I like it, I'm going to move the work plane around just to make sure it looks good. Grab all 3 components together, and I go up here and group. Notice those 2 now have disappeared. So that looks okay. May not be the perfect thing. One tip I have in Tinkercad is if you want something really small, use Tinkercad in a bigger form. You can always scale it down later when you're ready for that. So just kind of get the general sense of what you like in that particular view there. My next thing would be, that's my first joint, but if I'm making a finger, I probably need a couple more joints, right? Or a couple more segments of bone. So what I will do before I put that next one on, I'm going to go look for a connector. Over here, you can see there's different things that you can add to your designs. I personally like to just type in what I'm looking for. I'm going to type in ball connector. Okay. And when I have the ball connector, I can just grab it and pull it in just like I did my others. Now, I like to work overhead because I can see, a little bit better the perspective of how things are looking with respect to each other, and make sure that I'm getting kind of the dimensions that I'm hoping for. It's being a little finicky right now, so let's grab it and hopefully pull it in. All right, so this would be a little bit bigger than I would typically use, but I'm going to pull it directly into my drawing there. You see that? Now it's sticking out of one side, no problem. You can fix that as you go. I think I have it where I can squeeze it down now. Here's where, when you know that it's there, you're able to select it and then move it up. Notice I'm moving the orange one now. If you're having trouble grabbing it, you can move it aside again and do it from this side to make sure you're getting it at the right height. Notice when you click your object, if you're trying to move it up into the air, you will want to use that cone to go up and down. I particularly like Tinkercad because when you're using these, I can change my work plane, you guys. This is cool. I just hold down the W and it gives me a work plane. So I'm going to stick my work plane right on top of that first joint, right? See how the work plane has shifted? It's that orange now. If I click my other object, I can hit D and it will drop it, which in our case is actually lifting it to the exact plane of that given piece or wherever I put my work plane. Now, once it's there, I can drop my work plane back down because I don't want to be doing that. So now I can just center it into my object, and I know that I am at its level because we just did that drop, which was very accurate. Again, when you're doing your joints, feel free to kind of make this a little smaller as you're going because you won't need it that big, or you can make your base bigger, whichever is going to work best for you. I always go up to the top again, just make sure nothing shifted as I did that. And now that I have that component in and I'm exactly at that work plane, I'm going to drop it down so that it goes inside the finger. Okay. Because I want one part to be on this joint, but I want the next part to be on the other joint, right? Before I combine these, I'm going to take the first joint, get it exactly like I want it, and I'm going to copy it too. Remember how we did that? Just copy paste or Control C, Control V, and it pops out another one. I do that because then I can make it just slightly smaller. If you look at your finger, each one is kind of tapering. And that way I know I have the similar dimensions. And again, I can do that whole work plane trick where I hit W and I can get the work plane to appear at the top of this connector. And you would go through doing this whole part again. Now I may put the work plane down here actually, on top of that first one, because I want to make sure those two get oriented together as well. And then I will just move it straight up to the ball connector. Okay, and you can see I'm a little off right here, no problem. You can use your mouse. I find it best to be using a separate mouse and not the trackpad, but some people are really skilled with the trackpad too. So if that's you, go for it. All right, so I have it selected. And once I have it selected, it's kind of easier to select it in this view since it's stuck inside that first joint. And then again, we're gonna lift it. Just lift it up nicely. Now I'm gonna lift it right about there so I know I'm getting that joint. At this point, if you wanted, you could go ahead and add a little rotation to it. I'm gonna hold off, but this is where you would do that rotation. And then likewise, you would do a third joint, being that top of that finger. I would copy and paste this guy and make it a little smaller. Now, think about our fingers though. That might be too much. And it gets smaller at the top, right? Now, think about who you're making your finger for. Are you making it for a violin person? Do they have to have extreme precision where you're going to want to make sure the tip is long and slender? Or are they just getting to the point in their life that they just need to be able to button their clothes? So that will determine how you want to end the top of this. I mean, you could use some different types of ends, whether it be circle, semi-sphere, however you want to do that. You can elongate it depending on if you think it's a piano player, however you want to do that. Again, use those tricks about aligning from overhead, I find is the most helpful, as well as using that drop when you use your work plane, because I like to make sure that all my components are together and that they're, when I do it, I can just lift up or down. I don't have to worry about the lateral left or right movement. Okay, you guys, so you can kind of see the different components. So let's go ahead and finish it on out for you real quickly. What we'll do is to bring our third joint up to a new work plane. So first, let's raise that work plane up to the very top, bring our third joint up using the D function or the drop, and now we can slide it on over and start getting them more aligned. Let's check this out here. And that looks pretty good. Let's check our dimensions. One other tip I didn't mention earlier was that you can also clip directly on the views that you have on the left over here to help look at all 3D places around. All right, so I kind of like where that is. Now, one of the drawbacks of the connectors in Tinkercad, if I select this one, notice that it says the scaling is locked. So that's kind of a bummer if we want to make our finger bigger or smaller. There is a way around it, and I have it loaded for you. Let me show you. So I have exported that same exact connector into a file called Working C. Then you can go ahead and scale it. I'm going to scale it down to, let's say like 65% of what our current one is. As it imports, you will notice on the bottom left, it's importing in green, and here it just popped in. Now when I click this, it is scalable. So I can adjust it however big or small I want. Now, of course, that's ginormous and I don't need it that big. So I'm going to go ahead and just use the Control Z and go back. But I'm going to use this particular item now that I can scale it up in my next joint. Let's double check that we're getting that where we need. Okay, it needs to go over some. Double check. Okay. And I'm gonna grab it one more time. There we go. So that looks like it is nice and inside. Knowing that particular one is lined up with our work plane means that it is attached to the very plane that is sitting at the top of that second joint or the bottom of the third. So now I need to raise my third joint up slightly. And I'm going to go ahead and select it as well as its connector if I can get them both. And join these. For now, notice I used the group function up there. They all changed color to that purple now. And I want to drop. I'm going to drop that particular item down. So remember, we can't use our arrow keys. We have to use the arrow on the screen for this. This just makes sure that that ball connector is getting to our joint and not just sitting on top. Okay, now we can go back and ungroup and bring that third one up just a little bit so that it's on the other part of the connector. Very nice. All right, if we want to scale this whole finger, we would need to change out that piece, that ball connector that is not scalable. So I'm going to do that just for the ease of changing up things. If we have, a growing patient that's going to need fingers that are scaled. So I'm just going to pop that out. And the cool thing about Tinkercad, you can use the Control-C and the Control-V, and it just brings you another one right there. So I'm going to go ahead and bring it into my joint, just like that. Now, looking at this particular layout, it looks like this finger is really long, right? So I'm going to go ahead and try to bring all of these down slightly so it's not so elongated. There you have it. So now we have our different components. I like how that's turning out. All right. Lastly, we have to get that fingertip on, right? So let's go ahead and do that function next. We're going to put the work plane on that top of the joint. So this piece will then drop to that same height. Zooming in with my mouse, you can then start playing around with the dimensions of that fingertip. Now, I feel like this one is kind of elongated, like pretty elongated. So what I would probably do is shorten this up. I don't want a super long fingertip, but I want one that, can do the functions of whatever our person might need. They may need to be like, playing a violin or the piano, or be able to be pretty dexterous with that. So I'm liking how that's turning out. Again, you can adjust as needed. If you don't like having that lip there, remember you have these cutaways that you can go ahead and smooth that out if that's something that you or your patient feels that you need. And then from here on, I would just put some finishing touches. So for example, I would go ahead and select these two components together, group them, and I would rotate. Let's get those where we want them. Let's see if I can. And now that we have them together, just use the offset, just to offset it just a little bit. Oops. And then because we have rotated it, it came a little bit off center there, so you need to fix that as well. I like that, and I also want to go ahead and rotate that second joint slightly too, to show how your finger can move. Lastly, our very last part is how this finger is going to attach. So if we are planning to attach, we would need some kind of connector, right? The things that I recommend would be to go ahead and use the connectors that are already there for you. Here's a library, but again, if you just type in connectors, you can kind of see the different components. And I particularly like the ones towards the bottom. And we've already talked about how these shapes will match up exactly if you haven't altered them. So here is like a ball and socket that you can use. how about we go ahead and notice how nicely they fit together when they are connected appropriately. So we can imagine that this would be at the bottom of our finger. Let's rotate it around so you can see. The chain that would be like the bracelet that attaches can go through this hole and then down to the wrist of your patient itself. So we can go ahead and group these two. Once grouped, remember they cannot be scaled because they are set to match each other. However, all our other ones now can be. So I'm going to go ahead and select the finger, and since I want the ball connector to be underneath it, I'm going to raise it up ever so slightly to get into that last connector. And there you have it. There's your finger. Anything that you would like to shorten or scale is scalable now up until that connector that goes to the hand. Okay, so hopefully you enjoyed those Tinkercad tips and tricks. I want to talk a few minutes about inspiration for you guys. What are you going to create? Are you creating a finger or a hand for a child? Or are you going to create an adult finger? Which finger are you going to choose? Does it need to be the pointer finger? Because we use that one a lot, right? When we're stabilizing our pen or our writing. Or maybe you find that it's a construction worker you're trying to help and they need their thumbs. So check out the person that you are creating it for. Decide if it's going to be one of the middle fingers or the pinky finger. Once you have that in mind, what do they need to do with this finger? Like I said, is it that violin player that has to get that string just perfect? Or is it an elderly patient who is struggling just to button their shirts or sweaters? Think about what the person may need their fingers for. What are those needs that are specific that you can hone in on? Maybe they're a guitar player. Maybe they are a drummer and they just need to be able to grip well. When you think about that, you can decide what materials would be best. If they're a drummer, they probably need to grip very well. So something that has a little bit of friction to help hold that stick in so it won't slide out. Things like that. Those details are what make all the difference for your clients. So your next steps are, again, choose that finger wisely, decide how many bones and joints you're going to include, and then how you're going to attach it. If you like this, you might be interested in biomedical engineering. How can we help not just one patient, but lots of patients with our thoughts and ideas? And what can we create that's going to make their lives better? There are a whole bunch of free CAD programs out there for 3D printing. If you haven't seen them, check them out. Tinkercad is in them, but there's all kinds of ones out there. Some of them are professional ones where you would have to get a subscription, but a lot of those offer a free version as well. So take a look at those links. And then on the right, check out biomedical engineering as a potential field, or mechanical engineering, studying how all of the different motions and how things can move together, how we distribute the loads, and how we can use a muscle in the back of our arm to control our new fingers, things like that. Computer science, being able to dive into the details of being able to help code different responses if we needed. And mechatronics, this is I would say the joint of mechanical engineering and electronic, combining those things together. So if you're interested in either one of those, that would be a great option as well. And electrical engineering. Well, I hope you really enjoyed learning a little bit more about Tinkercad and how you can help change lives. I want to leave you with one thought, and this quote is from Richard Branson. He says that there is no greater thing that you can do with your life and your work than to follow your passions in a way that serves the world and you. And I think that just sums up this lab so perfectly, because you're going to use your passions and you're going to help people across the world. So good luck with your designs, take pictures and all of those good things. We would love to see what you create, and I can't wait to see you next time. On behalf of Engineering Tomorrow, thank you so much for your attention today, and we'll see you soon. Bye.